Pedro Barquinha, who got his PhD in 2012. He's presently working at the University of Lisbon, and his main expertise in the area of oxide electronics. And among several prizes, he is now running one of these ERC starting grants, and you can see the title of his talk. Thank you.
Okay, so thank you, and good morning. First of all, thank you so much for the invitation to talk here on this prestigious symposium. So what I'll try to do here is to give you an idea on what is the work that we want to do with this oxide nanoelectronics, and see that we are actually bridging this quite a lot with our previous experience in thin film electronics. So there's a lot of things that we can learn from previous technology that will help us to create the next generation of electronic devices. So this is our quite big group, led here by Professor Rodrigo, Professor Elvira as well here. And these are the guys that I'm presenting the work here today. Okay, so as I said, a lot of the things have been done in thin film electronics, and all these people are essentially contributing somehow to this movement from microscale to nanoscale oxides. So the presentation for today, I'll start by giving you the motivation for this topic. Why do we want this oxide nanoelectronics platform? We'll see that it's actually can be seen as a multifunctional platform that can be working not exactly to replace silicon, of course, but in parallel with that, to create really a multifunctional approach that can be used for several ends. And I'll show you also the first 10 months, so this is only started now in 2017. I'll show you what we have been doing, essentially learning from these microscale oxide electronics, starting to create our nanostructures, and starting to tune our electrical systems to deal with these oxide nanostructures. So, starting with the motivation for this, of course, you all know these interesting numbers from these first computers back in 1945. And in fact, miniaturization, as we all know, has been helping us to create much more from the electronics. So these days, these are typical numbers that we can find in processors, even for smartphones. So quite impressive when you compare them with these ones. And in fact, the main achievement to enable this has been the appearance of transistors. And we all know Moore's law, and in fact, we see that the number of transistors that we get per chip is constantly increasing, despite the fact that numerous times we've been listening to people from different fields saying that Moore's law is going to end and so on, and is somehow always progressing to include more transistors per chip. Still, you see that there are some things that are starting to happen. For instance, clock speeds are starting not to increase that much, and in fact, cost, which is one important thing in research, is starting to look not so promising. In fact, you see that the number of transistors that you can buy with $1 is actually not increasing for nodes below 30 nanometers. So I always like these numbers, making some extrapolation from conventional planar silicon electronics. And if we would go to this anniversary of integrated circuits, 2059, we would have these very impressive numbers that of course, they would be impossible to achieve with conventional silicon electronics. But the good thing is that this Moore's law is independent of materials, and in fact, we've been doing a lot of tricks in generation after generation to make it still survive. Just very brief examples, for instance, immersion lithography or multiple processing, where you get rid of these proximity effects which can kill the lithography at nanoscale. Transistor materials and architectures, where you use strained silicon to get better mobilities, FinFETs, and so on, to make sure that you can improve the current levels that you get in the transistors without using more area than you typically use. Stacked 3D, where you use the vertical direction to improve the number of the functionality that you can have on your chips. And then other things like parallel processing, or trying to live with the fact that we are putting things in smaller and smaller sizes, and we have to get rid of the heat that is generated. So people are using, for instance, integration of different blocks that normally have to communicate between them to make sure that they can cope with this. But the perspectives for this Moore's law handing are really looking like that we will reach to an end, at least the way that we know it. And in fact, we're talking about 2020 or something like that, where we end this Moore's law, where we get this 2 to 3 nanometer transistors, which will be highly unreliable because of these quantum limits and so on. Also, thermal limits and electrical breakdown, current leakage, yes, they are very big problems, but somehow, as we learned from previous generations, we learned to work with them. But it looks like we are really reaching to a point where we need new approaches for devices and materials to build those devices. So I'm not going here to different kinds of computing approaches or how you can deal with the massive amounts of data. I'm rather focusing on the material and devices perspective, okay? So, and based on that, we can have multiple approaches. Many more could be included here, but I would emphasize this 2D and 1D materials, which will be definitely very important for future generations of electronics. And even 1D materials, I like to emphasize this, that these 1D materials and alignment techniques, if we can really understand how to work with this, how to control diameters of materials that we synthesize, for instance, we can affect a lot of different concepts like single electron transistors, spin-based computing, or molecular electronics. So that's very important. And other things that are driving evolution is this so-called more than Moore concept. So rather than thinking about miniaturization only, people are very interested also in functionality. We don't really need the ultra-small transistor to make more of our electronics. We can think about adding more functionality into it. So you can actually put together these two concepts, and you can evolve in this sense, which is where I'm trying to get with this ERC grant. So essentially, we can see this more as not exactly as an end of the Moore's law, but as reinterpreting it in a different way. So essentially, adding value to what we give to a consumer that is buying electronics with this kind of concepts. So this made us think on what could be a cool idea to work with. And in fact, this is the goal of Trend, to get a transparent foil and try to put a lot of different electronic blocks into it that you can use for processing information, that you can use for sensing, that you can use for including energy harvesting, that you can use for showing information in a display, for instance. So think about a material platform that can offer you all this. So this was the driving force to think about this ERC trend. And of course, we looked into what the other materials can do. And in fact, of course, the silicon technology is people working in silicon technology are going into these concepts as well. Of course, there's a lot of work being done with transparent electronics based on silicon electronics itself. For instance, you get here active matrix for augmented reality applications that is essentially based on silicon technology, but this still requires a lot of transferring processes and so on. Or if you combine silicon electronics with a conventional thin film electronics, you actually have to find a way to interconnect the two different worlds. So we would like to make sure that we can use a single platform to do all this. And so we looked at oxides. And oxides, in fact, are being a tremendous success history, even in the case of oxide transistors. So we heard Professor Wagner yesterday about this, the time that it takes for technologies to be ready for production. And in fact, we heard numbers like 30 years or something like that for solar cells. And you see less than 10 years for oxide transistors to start to go from material research into commercial products that everyone can buy. So these days you can buy flat panel displays which have these oxide transistors in their backplanes. So that's very impressive for a recent technology. And what I would like also to emphasize here is that people have been looking at it as, until now, as simply a technology that can do some transistors to act as switches. But you can do much more with this. And in fact, this is another running ERC grant where people try to take thin film electronics into integration levels that start to be at least comparable to what people are doing in silicon. At least you start to plot a Moore's law, like a Moore's law to thin film electronics. So that's really showing that people want to do more with this kind of materials than displays. So you can really build electronics with this. Of course, the display industry has been having a big attention on this oxide transistor technology, and in fact, a lot of displays are already available with these oxide transistors, not exactly because of their transparency, but because of many other possibilities, like the fact that they can be processed at low temperature, having high speed, and very good uniformity in large areas. Then, to show you the very flexible platform that oxides can be, people typically talk about oxide transistors as indium gallium zinc oxide transistors. And when we think about new concepts for future electronics, we also have to think about sustainability. And of course, indium and gallium, as we saw also in a talk from about raw materials yesterday, are in this kind of forbidden area on this critical raw materials that we have. And hopefully oxides have many other possibilities. So you can work with many other materials that are away from this area, and you can still have very good performance. A good example that we have been exploring in our lab has been zinc tin oxide. So zinc tin oxide can also be used to create thin film transistors low at temperatures compatible with very cheap plastic substrates, and you can even create flexible OLED displays with it. So oxides seem to always have a good answer for different kinds of requirements of future electronic nodes. So if this is the case, why do we need a new concept? Why do we need this trend project? Well, the fact is that we want to bring autonomy, and let me tell you what I mean by autonomy here. We want it not only to be, we want the system not only to be, to have its own energy being harvested, but also not needing other kinds of electronic technologies to process the information that it needs. So you need electronics that operate quite fast. You need other things like thin film electronics to communicate information. So you need a lot of different things here. You don't want to depend on other material technologies. You want it to be sustainable, like different processing conditions. You don't really want to use exotic processing techniques. You don't really want to use expensive materials. You want it to be multifunctional. And so this is the way that this trend project appears. So we want to explore the multi-component feature of materials. So indium-free materials, low cost and temperature and scalable solution processing technologies. This is what we are learning with thin film electronics. We know that multi-component gives us a very large degree of freedom to tune the material properties the way that we want. It all depends on the cationic ratio that you want. You can tune the material for different kinds of applications, and we want to take that for nanoscale. We want to make sure that we precisely position these nanowires in the places that we want. And so that will give us a tremendous tool to work for integration on devices. And speaking about devices, what we're aiming here is transistors and generators. Transistors, we want to go from random networks that can be thin as a replacement for thin film electronics to provide even better performance than what we have these days, to these aligned arrays that can really give you a tremendous boost in the performance that you have. And then you want to put all this together into systems. So multifunctional systems that you can work with, like I said. So where are we now after these 10 months of implementation? Well, as I said several times now, we are learning quite a lot from thin film electronics. We are working, of course, as I will show you, on some synthesis of nanostructures. That's our basic materials to work with. But a lot of these material knowledge, device physics, circuit and system design and integration techniques, we are grabbing it also from thin film electronics and adapting it to the different concepts in nanoscale materials. Let me give you just some examples. Miniaturization of microscale oxide transistors. We are taking these to the limits of our current photolithographic techniques, down to 1 to 2 microns. And we see that, as we expect, the cutoff frequencies would increase, so this would give us potential to do faster circuits with it. But then we have to understand, when we go to small dimensions, if our devices behave as we expect, and we see that they don't. We have the so-called short channel effects playing a role. So we need to go to our TCAD simulation. So there's a PhD student working quite a lot on this to understand what kind of short channel effects we have that are affecting the properties of our materials. So these are just different things like drain-induced barrier lowering or charge sharing that I showed here in this slide. But the good thing is that the message that I want to give here is that if you really understand what's going on here, you can get rid of these effects. And this is just an example on devices that we can fabricate today with different structures, with different material combinations, where you can go down 1 order of magnitude on their device sizes, and we don't have these short channel effects, and you can operate them actually with very low operating voltages. So we're getting to the thing that we want. But then we are also talking about low temperature electronics. Even when we move to nanostructures, we want to keep low temperature. And we know that low temperature will always give us a very high degree of instability. And of course, we want to optimize it as much as possible, we want to understand it, but somehow we'll reach to a point where we have to live with it. So we have to find ways to design our circuits in a way that they can cope with the instability that we have. So this is a very simple example where devices are unstable with bias stress and with measurement, but you actually can design this in a way that your circuit is not sensitive to that. So we are taking these concepts to nanoscale now. So of course this depends on having a platform englobing device modeling, involving circuit design and simulation, and involving layout design that we are constantly upgrading. And this is enabling us to make also systems with this. Not only individual blocks, but combining it into systems. So there's already a quite complex system for thin film electronics. We're speaking here about between 150 and 180 transistors that are integrated to make this concept works. And so this is essentially on an interactive packaging model where you can monitor fill level sensing and temperature of a beverage that you have. And the reason why we want also these short channel transistors that I talked about is because we also want to make this kind of technologies, high PPA displays or flexible RFID tags that work as fast as possible. And then, just to show you some of the work on the nanostructure synthesis that we've been doing. Of course, there's a lot of work published already on zinc oxide nanowires for quite a long time, but most of it relies on very high temperature processing to get good properties. So in our case, what we are doing is to use these low temperature processing techniques like this hydrothermal synthesis that with combined effect of temperature and pressure enable you to get a lot of different oxide nanostructures. So these are different oxide nanostructures that are already being synthesized in our lab. Let me show you the ones that are relevant for this trend project. This is zinc tin oxide, the material that I showed you before that we synthesize in thin film form. We are now able to make nanowires of this at temperatures below 200 degrees. And the good thing is that we can control the properties of the nanowires that we have, adapting it for a semiconductor, for a piezoelectric material, or something else, depending on the composition that we can have. So that's a very good tool to work with. And you can, just to show you a last example, you can even think about different ways of synthesizing it while keeping the low temperature. You can grab a 85 degrees very straightforward process of making these zinc oxide nanowires, and then you can convert them to different kinds of structures of ZTO. So it's the same material, but having completely different structures. For instance, you can create this hollow or solid ZTO depending on the synthesis conditions that you use. You can use this for photocatalytic activities, for instance. You can use this for semiconductor activities. So there's a lot of things that you can do with this. And just a final slide about tools. So measuring these things at a nanoscale level is not as easy as it might sound. And it's very easy to get wrong results. So we need really to understand, we've been devoting quite a lot of time, me together with my PhD student, we have been devoting quite a lot of time to understand how we can reliably measure these things. And today we are able to have reliable electrical measurements of these isolated nanostructures. So with this, the take-home message is that these nano oxides are much more than electronics. There's a lot of breakthroughs that need to be done during these next 4 years to make sure that we can do everything that I'm trying to promise here. But I believe that this can affect many other different fields, not only electronics. You can even go for living cell interfacing or structural nanomaterials. All these control of nanostructures will enable us to do this. So thank you so much for your attention.